Hey guys, welcome to Cougar Chem Tutoring. I'm Austin. I'll be running through part 2 of problem set 5, light. All right, number 6. What is black body radiation? Black body radiation is light or radiation emitted by an opaque, non-reflective object. Okay, opaque, non-reflective object. And this is specifically at high temperatures. And you'll kind of recognize some of this, right? This is lava, right? Lava is a very good example of black body radiation. When it gets really hot, you know that this part's probably super hot, right? Because it lights up a lot. So light is emitted when a particular object at high temperatures is reflecting it back. So another example of this would be like your stove. Like if you have an electric stove, if you've seen it kind of light up red or orange or even like yellow or blue sometimes when it gets super hot, right? And that's an example of black body radiation. Now there's a kind of a spectrum of black body radiation. You can be kind of a good black body or not a good black body. The only difference is how well you're able to reflect back. It just so happens that stars are like almost perfect black bodies. Like the sun is a perfect black body. And there are things like lava or our stove that aren't perfect black bodies, but are enough to give us a reflection back of some of that radiation. All right, the temperature of a lava flow can be estimated by observing the color of the molten lava. Based on the color temperature scale generated for hot metal being forged to the left, estimate the temperature of the hottest part of the lava flow in this picture. Okay, the hottest part. Okay, let's say that's going to be based on the brightest part, right? Because the brighter I go, the hotter it gets. So let's look. Let's say right there, or even just right there, and that's pretty close to, I don't know. And arguably, you could say that's somewhere between 1,000 and 1,200. I'll just say maybe let's just say for simplicity's sake it's 1,000. Whoops, not 10,000. 1,000 degrees Celsius, or even somewhere between that and 1,200 degrees Celsius. Okay. All right, black body radiation can also be used to study stars. If a star A radiates a light with maximum intensity of 660 nanometers, and star B with a maximum intensity of 475 nanometers, which one appears more blue? And to be honest, all you have to do for this one is to look at the electromagnetic spectrum. So here, I know that one was about 600 something, right? So that makes sense. It was 660, and that's in the red region, right? And then the other one was 475, which was somewhere right here. Yeah, so it looks like star B. Star B is going to be the one that's emitting more blue, because it's more within that spectrum, in the color spectrum. All right, B, which radiation has the higher frequency, the red light or the green light on a traffic light? All right, so let's go back up to this electromagnetic spectrum. So if I look at this, let me erase this here. Okay, red's usually down here next to 700 or 600. Okay, and green looks like it's right here. So which one has a bigger or a longer wavelength? Red does. Red has a longer wavelength, but having a longer wavelength, let's say lambda, is not equal to higher energy. Okay. It's equal to lower energy. Remember the inverse relationship that we talked about? So in theory, when we're talking about energy here, the green is going to have more energy. So the more you go this way on the electromagnetic spectrum, the higher the energy. In fact, if you look here, X-rays, gamma rays, those are some of the highest energy photons that you can have. Okay. So if I go back, it's asking which radiation has a higher frequency. Higher frequency has higher energy. And we knew that the red hot light had a higher wavelength, which means it has a lower frequency. So that means, in this case, it's going to be green. Okay, the green light. That's going to be our answer. All right. The work function of a material is the minimum energy required to emit an electron from the material. If the work function of Ag, which is silver, is 7.59 times 10 to the negative 19th joules. Okay, so this is the minimum energy that a photon has to have in order to knock off an electron. Okay, so let me kind of demonstrate what we're doing here. Let's say we have a sheet of metal, and this is going to be our silver. So this is a sheet of metal, silver metal. Okay, what we're doing is we're shining light at it. So let's say I have a flashlight here of some sort. Pardon my non-artistic ability here. We're shining light onto it. Okay, and then these photons are hitting the surface, and then based on if they have enough energy here, then they can knock off an electron. Okay, now this is actually super important in real life because this is, you know, how we do a lot of things, including like solar panels, right? Solar panels are based entirely off this idea where we have light coming off from the light source of the sun. They knock off electrons, and then we use these electrons for electricity. Okay, so that's what we use solar panels for. This is kind of an example of that. Okay, so the work function, all it is a threshold of energy required per photon to knock off electrons. Okay, so in order to solve this problem, what we have to do is determine if the wavelength of each photon exceeds or is below this threshold right here, to see if it will knock off electrons, okay? So what we do is say, okay, I know that E is equal to hc over lambda, giving that I have a wavelength, okay? And then I know that this is equal to Planck's constant, the 6.626 times 10 to the negative 34 joules seconds, okay, times 3 times 10 to the 8th meters per second, the speed of light, divided by 250, okay, times 10 to the negative 9th meters, okay? Meters, seconds cancel. So I'm going to get an answer in joules here. And if you multiply those together using sig figs, negative 34, 3 to the 8th here, divided by 250 to the negative 9th. All right. I get about 7.95 times 10 to the negative 19th. Okay. Now, is that enough? Is that enough to eject electrons off of this? This is definitely a bigger number than that, right? Not by much, but it is bigger. So yes, will electrons be emitted from my earrings? Yes, because we've exceeded threshold, which is the work function. The work function is that threshold. So I've reached at least 7.59 times 10 to the negative 19th. In fact, we could even subtract this and say, okay, how much energy would I have left over? And this will be important for when we start doing the actual work function equation, because they'll ask us to kind of find these differences because it'll actually turn into the energy of something else, which we'll cover here in just a second. Okay, so this would be, the difference here would be 3.6 times 10 to the negative 20th joules, okay? And that's how much energy is left over. Now it says if radiation hits me that has more energy required to emit than an electron, what happens to the additional energy, right? This is the excess energy I had, right? I met the minimum, but then I exceeded it, okay? And I had this much extra. And that all goes into the kinetic energy of the electron. Okay, so having the extra energy there just gives that electron more kinetic energy, more movement, okay, in that equation. And here we'll kind of apply that even more on number 9. Okay, steel and iron are often galvanized or coated with a thin layer of zinc metal to prevent corrosion. Iron rusts, but zinc does not. What is the lowest frequency of light that can eject electrons from zinc metal? Okay, so it's kind of key to understand this phrase. What are they saying with lowest frequency? When we have the lowest frequency, that's usually what? The lowest energy as well, right? Lowest energy. So what they're asking for is what is the minimum energy of light that ejects electrons from zinc metal, but in terms of frequency, okay? A lot of times, so this is actually synonymous with longest wavelength. If they use any of these phrases, they're talking about the same thing, okay? Lowest frequency, lowest energy, longest wavelength. They're just talking about the minimum amount of energy that is required. And what that means is we're literally trying to find the value based off of the work function here in terms of joules to determine the work function itself. So really all we have to do is say 4.3 electron volts times 1 electron volt here, 1.602 times 10 to the negative 19th joules. If you do that, we're going to find out the literally just the work function of zinc, which is the minimum amount of energy. That's going to be our lowest amount of energy required to eject an electron off of the surface. So here would be, say, about using sig figs, about 6.9 times 10 to the negative 19th joules. Now, this is the minimum amount of energy, but they asked for it in frequency. So then I would have to say 6.9 times 10 to the negative 19th joules And then I know that E is equal to what? H nu, or hc over lambda. In this case, I'm looking for nu, so I'm going to divide this by Planck's constant to get nu. And then if I do that, I get 6.626, negative 34. Okay, just to keep track of the units here so you understand, my joules are going to cancel. I'm going to end up with 1 over seconds, right, which is what I need for frequency. Here I get 1.04 times 10 to the 15th hertz, or 1 over seconds. Okay, so that's the lowest frequency. If they'd asked you for the same thing in terms of wavelength, you would have just said, okay, hc over lambda instead, and then done the same thing. In this case, I guess I could just divide by, or take the speed of light and divide by the frequency here, because I'm pretty sure for your problem, they actually did ask you for the longest wavelength instead. So for you, it would be 288 nanometers, okay, or 2.88 times 10 to the negative 7th meters, okay? So that's kind of how we're going to use the work function. Remember, it's just a minimum threshold. The work function is just a minimum threshold. This is the minimum amount of energy required to eject an electron, okay, right? And then we just found it in terms of lowest frequency, and in your case, longest wavelength. And that's how we were going to work with work function. And then any extra energy that we exceed past it, if the photon has more energy past the threshold, then it's going to turn into kinetic energy for the electron. And it's going to be evident in this following equation. It's going to be equal to, this is called phi. Okay, phi is the symbol for the work function, is equal to h nu minus kinetic energy of the electron. Okay, and you'll use this equation mostly for exam 1, and you'll want to know this is the energy of the one photon, energy per photon. And then this is literally just the kinetic energy of the electron, and this is the work function, which is always in terms of joules as well, so in joules. All right, cool. Well, I hope that was helpful, and we'll see you in problem set 6.